Hey everybody, how's it going? Welcome back to Jai with Judah, the video series where we talk about the Jai programming language. In this video, we're going to be talking about operator overloading, what it is, how to use it, and some potential limitations and foot guns you might run into while you're using it. So, if you've never heard of operator overloading before, it essentially allows you to create overloads for operators in the language for custom data types you've defined. Put simply, it allows you to use math, logical, bitwise, and these miscellaneous operators for structs in your program. So you might be thinking, why would I want to do this if you've never dealt with it before? It allows you to improve the usability and sort of, I don't want to say aesthetics, but it's essentially the aesthetics of working with some data types. If you have come from C++, you probably know all the horribleness and foot guns that C++ allows you to do. You know, for instance, the very standard std C out, hello, std and L stuff it allows you to do, right? This is operator overloading in C++. Jai's operator overloading is a little more pared down, a little more sane, so you don't have to worry about it too much. However, like all operator overloading, you can do some crazy nonsense, and we'll talk about that later in the video. So the first example of how to do this, we're going to be using a vector2 type, which is a pretty canonical type for operator overloading. So a vector2 type, we're talking about the mathematical vector type, which is a type that has two components, in this case x and y, which are both floats. There's also vector 3s, vector 4s, quaternions, all that stuff, which could be thought of as, a vector type in this case. This could also be called a point, but we're going to be calling it a vector2 for the sake of this video. So if I create two vectors, right, like so, vector 2 of 10 and 10, and then b vector 2 of 1 and 1, right, I have these two vectors, and let's say I want to add them together. So I would normally have to do this, a.x plus b.x, y is a.y plus b.y. And if I print that out, you'll see that we get the value we expect of 11 and 11, right? So component-wise addition of two vectors, right? If I had to do this by hand every time, this would be very annoying, and I probably would try to find some way to simplify this, and most people do. So they'll usually do something like this, right? Vec add a and b, and that will return a new vector with component-wise addition. But Jai allows us to do something like this, which just, does the exact same thing, but we can define how that works for a custom type. And the way we do that is we simply define a function for that operator that has the parameters that we would want and the return type we'd want. So if I do operator plus, I'll do the left side as vector 2, the right side is vector 2, and it returns a vector 2. And now all I have to do is rewrite that code I did earlier, right? r.x and l.y plus r.y, and this will now work as we expect, right? So now we have this operator plus for our vector 2 type. And in Jai, with simple math operators, binary math operators, we also get the the operator equals version of that for free. So if I do this of 1 and 1, you'll see that we now get 12 and 12. If I defined multiplication, we'd get that exact same thing for free. Now, this plus equals operator was auto-generated for us. We could very easily do this if we wanted to control how that worked. So we'll make it pass by pointer in a vector 2, right? And we will just simply do l.x plus equals r.x, l.y plus equals r.y, and this will work the exact same. We also don't need to return a value, and that will work exactly the same, but we control how this works, right? So there's no magic going on behind the scenes for how this is working, right? We can see the code that it's actually executing. So another thing we can do to improve this example is to add in, an alternate viewing of our vector type. So vectors, when you're working with them, sometimes it's nice to treat them as an array of two values rather than a struct of two values, right? So for instance, let's say I wanted to do some array programming, and I wanted to do C0 equals 10, and C1 is 20, right? And I want to use my vector for that. Well, I would probably have to do some funky stuff, right, to get this to work properly. I might have to do like, we'll make it D, do like vec to array, and that takes in a pointer to a vec, that then I can do, this to modify it. But we can actually simplify this even more to get that original functionality that we talked about. And we do that with these, well, I've put them under the miscellaneous category, but it's operator index and operator index equals. And these are actually a special case in Jai, and I'll talk about why they are in just a second. But before we do that, let's add an alternate viewing of this data type. So I'm going to do place x components is 2 floats, and I'll make sure it's uninitialized to show this is a fake member of this struct. In Jai, this place directive essentially means treat the address of this value, or treat in this struct the offset of this value as this data type, right? And in reality, this will treat the next n data types until you get to the end of the this final member. You don't have to understand this fully right now. You can essentially think about it as just a union that has some struct x float and y float like this, and then it has an array of 2 floats, right? That's essentially what this is doing, but there is some syntactic sugar to make it, not awful to work with, and extend a struct rather than changing its structure to fit how we want it to work. So let's add that operator overload to make this work. So we have operator index, and that looks like this. So we have our vector2, and I'll make it just v for vector. Then it'll take an index, which is an integer, and then it will return the component type, right, or the expected type that we would want for this. And all we have to do to get that to work is just return v.components index, right? So all components is just viewing this x and y as an array of 2 floats rather than a struct with 2 members. And so we also have to define another function overload for this, and that will be operator index equals, and that just simply looks like this. It takes a vector or a pointer to some type, takes an index, and then it takes a value. And it doesn't have to return anything. You could make it return something if you wanted it to, but it's a bit weird and not the best idea. But there we go. So now if I run this program, you'll see that we get 10 and 20 rather than 12 and 12 like we did a second ago. And a quick note on these operators: these are a special case. So Jai will try to automatically generate these operators if I define one. So if I defined this one, Jai would automatically try to generate this other one, and vice versa. However, because we are accessing a fake member that we've defined, right, just an alternate viewing of the data on this struct, it doesn't know how to generate that, right? It doesn't know what we actually want it to do. So we need to generate this, or we need to write this manually to get it to work the way we'd expect, right? And you might also be thinking, oh, geez, so I'm going to have to write all of these operator overloads for, vector types. Usually I have a vector 2, a 3, a 4, and so now I'm going to have to copy and paste this and do all that nonsense. Well, you don't actually have to, right? You can take advantage of Jai's insert and run. This is the syntactic sugar to do insert run. We could also do that. But this is just syntactic sugar to automatically generate code at compile time, right? So for example, we could say operators is, an array of strings. That's plus, minus, multiplication, and division. And then we could simply iterate over this operator list, generate a string that's just all of these operator overloads, including the array indexing and all that stuff. And then we wouldn't have to deal with, manually writing this all by hand. And if you really wanted to go crazy, you could also generate all of your vector types at compile time to have, some arbitrary number of components. The sky's the limit with this. But there you go. That is our vector example and how we can do some operator overloading to make vectors easy to use. Now let's go into some of the fun parts of operator overloading. So early in the video, I mentioned that you can't do something like this, that you can only define operator overloads for struct types, that you can't do it for primitive types like strings. And you'll see if we compile this, we get operator plus does not work on strings. And that is a limitation hard baked into the compiler to make sure you don't go too crazy with operator overloads. However, there is a way to get around this, and I'll talk about that right now. So let's just do a dynamic string class, dynamic string type that will allow us to do what we wrote a second ago. So we have this dynamic string type, and now all we need is a way to convert a jive string into our dynamic string type, right? So I can do to dynamic string, and I'll do no stir, and that returns a dynamic string. And all we have to do is go value equals s. If I can, type properly for once. And there we go. So now we can do whatever we want. Now that we have successfully put the string inside a struct, we can now define any operator overload for it and make it do whatever we want. Right? So let's get that example to work. So we'll have, buff is to dynamic string. And we'll just say, we'll make it empty for now. And let's be a little responsible with our memory allocation. Let's take an allocator. Let's put an allocator on this struct as well. We'll do allocator equals allocator. And so now that we have this, let's add, a free dynamic string procedure to make sure we're being, like I said, responsible. If we're going to be doing something weird, we might as well be responsible about it. So we should do this, free d.value, allocator is d.allocator, right? So now this will compile, but we haven't added the fun part yet, so let's do that. So let's say we just want to do a simple append, right? So we'll do a plus equals, and then we'll do, another plus equals, and that'll be, world, like this. So all we have to do is simply go operator plus equals for our dynamic string, and we'll make it take a string, like so. And this is very simply just going to do d.value equals join d.value, s, and allocator equals d.allocator. And now if we compile this, it will actually let us do it, right? So we can go here and print our buffer, and we get hello world. So we have successfully added string operator overloading to Jai by sort of abusing the system. And I'll talk about how we abused it right now. So I did say we can't create operator overloads for strings or for primitive types. However, if one of the arguments in this operator overload procedure is a struct, then we can, right? Then we can make the other argument some arbitrary type that's maybe a primitive, and it'll work as we expect, right? Now, I would not rely on this behavior to exist long term. I will assume this will get taken out later down the line, but we can do it for the time being and take advantage of it and do gross things like this. So let's quickly make this example even more fun, right? So let's say we want to do, substring, like if a substring exists inside our dynamic string. So let's say if world exists in buff, right? We want something like this. But of course, in is not a valid operator. So like you saw a second ago, I'm going to use the caret. We can actually get this to work, right? So I'll print and I'll say world is in our string. And so how can we do that? Well, just like we did a second ago, we can create an operator overload that takes a substring and our dynamic string, and it returns a Boolean. And all we're going to do is just do return contains d.value substring. And now if I run the program, we'll see world is in our string, right? So now we've done some gross stuff where we've added in an operator overload to do, this contains. And you can really, the sky's the limit, like I said earlier with this system. But you're also probably wondering like, hey, string is the first argument and this dynamic string is the second argument. Why does it still work? Well, the above rule that I said earlier still is in effect, right? As long as one of the arguments are that struct or is that struct, then it will allow you to create the operator overload, or it'll actually allow you to do that, right? And like I said, don't rely on that, but it will work. So the final thing I want to talk about with operator overloading is just a fun little quirk you can do with it because of how they work in the language. So let's say I just want to create a new, well, actually, we'll use this operator question mark. This is a perfect example for it. So operator question mark partially exists in the language. And we'll actually do it like this, right? So if I try to do world question mark buff, you'll see that we get an error that says the question mark operator is not yet implemented. Maybe it won't be. It doesn't exist or it isn't used, but we can still define it for a type. So if I change this to operator question mark instead of operator caret, you'll see that it still fails. However, we can get around this by calling operator question mark like a function, like so. And if I run that, you'll see that we get the same output world as in our string, which means this is working as we expect. So operators in Jai can be called like functions, like so, right? Simply writing operator and then whatever its name is as a function and then passing the arguments explicitly, right? So that is something we can do. You might be wondering why that's a thing. I assume it's most likely because of a directive called bake arguments or another directive called procedure of call. These are two directives that take a function call and will bake arguments in at compile time, so that way you can create more dynamic or you can essentially hard bake in values at compile time rather than making them be passed in at runtime, which is pretty useful in some cases. I'll talk about directives in another video, but for now that is why I think they're mostly added in. But yeah, thank you so much for watching. This was operator overloading. Hopefully this answers some questions. I'll leave this on the screen so you can come back to it, at a later point in time. But I have marked these off into different categories so that way you know what they're used as. Some of these are undocumented. For instance, these, right or three less than symbols. These are actually unsigned shift operators. So we have unsigned shift left, unsigned shift right, unsigned shift left equals, and unsigned shift right equals. And then, of course, these are, shift left and shift right, as you would expect. Unfortunately, you can no longer overload the dereference operator like you could in the past. I think it makes sense, but it was something you can do in the past. But for now, there's no way to currently overload dereferencing. Maybe there will be in the future, but who's to say? Anyways, thank you so much for watching. Hopefully you enjoyed the video, and I hope you all have a great day.